like, and what is the connotation that mentioned by ITU in terms of sustainable development for 6G. So that will help us to understand how can we come up with indicators in technology or operation and maintenance. And also, we also need to understand sustainability is not just achieved through low carbon or zero carbon, but also through many other interactions and application scenarios. So we need to understand what is sustainability, sustainable development. This is a common goal shared by the humanity. In 2015, when the then president of China attended the General Assembly of UN, he made a speech referring to the 2030 Sustainable Development Goals, the 17 goals. So sustainability is the single biggest agreement point that has demonstrated the same the interest to each and every countries in the world. So that is also the area that we need to carry out international cooperation. So what is our common goal, and how can we bring prosperity through the sustainability to the world? So then Secretary General Ban Ki-moon talked about the common vision. So the sustainability, the 17 goals are the common vision of the humanity, and also is a social contract, and that world leaders and the people agree on that kind of social contract. So shared by more than 7 billion people. So the 17 goals are very important. So we can understand in this way. So including elimination of the poverty, zero hunger, and also the equality in education and in gender, and also the protection of the life below the water and on the ground, and also the mitigation of the climate change. So you can see it covers economic, environment, and social dimensions. Then the 17 goals are interconnected. It's not separated. You cannot achieve sustainability through either single one of them. So because we need to look at it in a comprehensive way or integral way. So when we think about 6G, we also need to think about in that dimensions. So the 17 sustainable goals are interconnected or defined in 3 different dimensions, but there is a core issue, that is we need to achieve human welfare, and at the same time we need to protect the planet. And there is actually a core conflict here. So when we want to achieve human welfare, better education, zero poverty. At the same time, we also want to provide the diversity of the life on water, under the water, on the ground. So there's a kind of a core conflict between the balance of the human and the nature. And so, for example, that's why we try to resolve the problem by coming up with or using the renewable energy or the innovation of industries. And so you can see those are the linking goals. So that goal connect or balance the welfare of the human being and also the planet. And also in the next generation communication system, of course, at that time in 2015, it doesn't mention something about 6G, but it mentions about we need to develop the next generation communication system. So the core issue for us is to protect the planet. Currently, the biggest threat is the climate change. Last night, I watched some TV news, and there will be a very strong wind coming from the north of China. Some people say it's going to go as high as 12th grade of wind. So that's something related to climate change. And also here you can see the change of the climate since the industry revolution from 1850 to 2020. You can see IPCC, the Intergovernmental Partner on Climate Change, has 6 task forces. The first one is the task force on providing the scientific evidence for the climate change. So there are a bunch of engineers from different countries. They observe the climate change variant from 1850 to 2020. And you can see the temperature change percentage is fluctuating. You can see the black color line. And before the World War II, you can see we observed that the change is zero, even there is fluctuations. But after World War II, especially after 1980s, you can see there is a systematic drift upward. And by 2020, you can see according to the Paris Compact, we see that we need to control the temperature within temperature change within 1.5 Celsius degree. So what lead to the climate rising? We have this simulation, and you can see the brown one, which is very close to the black one, which is a real observation. And you can see the confidence level range is 90%. And you can observe all the temperature changes have been covered by the simulation as compared with the real temperature change. And also in the simulation, we eliminated, if we eliminated all the factors like the emissions of industries, emissions from the agriculture or transportation, and also eliminate like volcanoes or the earthquake, and then you can find it's still fluctuating, and the fluctuation average or mean average is still within or it's aligned with the real fluctuations. So you can see that is a very key threat for mankind. The United Nations called it as a red code alarm. So if human beings don't cope up with the red code alarm, humanity will be walking towards the final destruction. So you can see the human existential conditions hardly come by. Over the past 1.1 billion years, there is the generation of three layers in the air. One is atmosphere layer, and also there is the rock layer and also the water layer. Those are all essential elements for human survival. And after about 300 million years of evolution, we saw the soil layer and the bio layer. And about 2.5 million years ago, if we say the human civilization is only 5,000 years, you can see 2.5 million years ago, that's how we generate those kind of different animal civilizations in the world. So it's very important to protect the existing conditions for mankind, also for the animals. So that's something every human being needs to do, no matter what kind of industry we're committed to, or even 6G. So in 2015, there was this mentioning of the protection of the planet, and the 2030 is the end, the deadline, right? So in 2023, there was an assembly by the United Nations. It reviewed the past 8 or 7 years of progression, and you can see there's different color blocks, and if the color is more deeper, that means we are more far away from the target or the goal. And you can see the predictable targets are actually unchecked. Many of them are unchecked, and 30% of them have no progression for the betterment. So you can see the two green blocks are related to communications. For example, the popularization of internet. And the COVID even accelerated the development of internet, right? So currently, we need to think, how can we use the internet to support the green development for the communications? Last year, UN has another meeting, which is called the Summit of the Future, and come up with the pact for the future. And it talks about the digital global compact, which is related to 6G. And on the very first paragraph of the digital contract, and it says that the digital technologies is disrupting our world, and it's essential for us to achieve our sustainable goals. So when we are developing 6G or 6G goals, we need to think about how can we contribute to the sustainability and also green development globally. So the Global Digital Compact has this kind of a requirement for all of us. This is also a common compact shared by the humanity. And also ITU mentioned the requirement for the green 6G or green communication. So we need to reduce the emissions of in the communications. When we are reducing our emissions, ITU also required that the development should contribute to the low carbon goals or the green development, and also ask us to satisfy the sustainability goal, right, in the life cycle. And so the 6G development or design, its module design, its system structure, all needs to consider the power consumption, the energy, because power consumption is one of the key contributors for the climate change. In the past, we finish everything, the design, and then we start to consider about the power consumption, right? But now we are more energy aware from the very beginning. So we have higher awareness than before. And also frequency is a very important natural frequency, for example, terahertz. Now it's a very rare resource, but in the future it will be very important resource, and it's limited resources, right? And so when we're using the different materials for the hardware or for the system, we need to consider recyclability. It should be environment friendly. And also a key factor here is we need to consider how can we reduce the carbon emissions through the using of the materials or recycling. And we actually have quite a lot of experiments related to the carbon emission reduction efforts or measures. So the communication system carbon emissions will account about 0.4% of global carbon emission by 2030. And currently, you can see the emissions are increasing. I hope with the introduction of a 6G, the increasing trend can be reversed. We want to turn those core values or requirements of sustainability to our KPIs of 6G development.
Sorry, this is not my updated version. Therefore, we need to design many indicators, and we have tested them, and we hope that ITU and 3GPP, like energy efficiency ratio, we can properly design it. So I was thinking if I maybe every bit below like 0.1 joule or even lower joule. So I put a question mark here. All of this could be considered and better designed. And also the carbon intensity as well as the repeated use of the device and also the lowered energy level, etc. So this might require more systematic discussion, and there needs to be a number of technical indicators or design some lab testing for the technology. And so those are required for our work going forward. And if we're going to get there, first of all, we need to properly design the standards. And secondly, it is important to establish the all life cycle testing assessment of the usage. So if I'm going to use the 6G system, how much energy level I'm going to consume, and for that amount of energy level, when it's being used in the production, and the overall energy level would be reduced. And so for that, there needs to be a global consensus. I read about some report that the system designed by Nokia, they have done the experiment that AI could be built in to lower the energy level by 30%. This kind of experiments should be collaborated under the unified platform of global collaboration so that it could be translated into some technological standards, technical standards. So regarding the specific application scenarios like smart cities, So for smart city scenarios, we can provide smart lighting, green buildings, for instance, to achieve the energy level reduction. So in Korea, Incheon, Korea, there is an example a case study that they build smart cities, and by providing smart lighting and green, lower the energy savings could be achieved by 30%, could be lowered. And through smart as industry, we can leverage digital twin to reduce industrial waste. There is a Siemens report that smart industry was being developed, smart manufacturing was being developed to improve elevate to 25% of energy efficiency. And also, if we look at smart farming and autonomous driving, all of that scenarios could be leveraged with the help of 6G to lower water usage as well as transport emissions. Therefore, we need to identify some enablers for sustainable 6G so that it could be low carbon and green. So there would be multiple layers. So 6G is very much scenario driven, and when planning this 6G, we have to consider all of the indicators, and then we can also consider developing the green green certificates, as well as maximize the application of renewable energy. And one of the important things is international collaboration. Now, as we move to 6G, well, despite the geographical uncertainties, we do hope 6G is a global scale system that could facilitate global growth. So we have strategic layer, technical layer, application layer, and global collaboration for a global partnership. So I want to sum by saying that 6G must not only connect the world faster, but also preserve it better. Thank you. Thank you so much, Mr. Gong, for your very insightful opening presentation around our topic 6G for green and sustainable development. Next, I'm going to invite our next speaker. Is from Nokia Bell Lab, Finland side lead, Dr. Mikko. Because of international travel issues, Dr. Mikko will join us via video presentation, and he will be discussing with us the latest research development in this particular field.
Hello, I'm Mikko Uusitalo, coming from Nokia Bell Labs Finland, being Nokia Bell Labs Finland site lead, as well as leading a radio research department here. And today I'm speaking in my other role as leading the European level 6G flagship HEXA-X2. And it's a great honor, pleasure that you invited me to contribute to the Global 6G conference. It's a pity I'm not able to be physically there, but pleasure then to contribute via recorded presentation. So let me go to my presentation. As you can see, I'm talking about sustainability and especially on sustainable 6G and 6G for sustainability, so the two main dimensions of sustainability and 6G. So 6G itself needs to be sustainable, and we need to see how can we use 6G to improve sustainability in other sectors of society. First, couple of basic words about HEXA-X2, so maybe known to many of you, but good to bring everybody on the same page. So yes, we are the European level 6G flagship funded through smart networks and services joint undertaking, big consortium, 44 members, Nokia, myself being as the overall leader, Ericsson in a technical manager role. Here also you can see how widely we are covering the different parts of the value chain as a consortium. So we have R&D intensive operators, we have different kinds of technology providers, high quality academia. We are basing our work on sustainability, and here we should understand sustainability widely. So we are looking at possibilities to impact, contribute in all the United Nations Sustainable Development Goals. As it's great to see many other activities around the world also looking at the 6G and other future technologies. So we have also introduced, from our perspective, human and planetary goals, even better fitting this domain, fully linked, aligned with these United Nations Sustainable Development Goals. And you will see more information about these goals later in the presentation. Overall, in HexaX2, we have been having a new look on 6G use cases, services, requirements. We have been developing technologies needed for 6G, and especially then bringing these things together to build this 6G system blueprint and platform, also signaling what is really important for 6G and what not, and how do they relate with each other. We are releasing a new system blueprint around every half a year, and now in the near future going to release the latest version, and I will also show a bit on that in the end of the presentation. And we are interacting in Europe and also internationally with other activities and projects to align globally the views. I'm not going very much in depth of this, as I showed this already last year, highlighting here just that worldwide there is quite big alignment in the direction for 6G, lots of similarities, and where there is maybe biggest differences is in the area of sustainability, where all the activities are recognizing the importance of energy efficiency, carbon gas reduction also to some degree, but then the wider look at sustainability is usually a bit missing. So we need to design 6G to deliver value and to be sustainable. And here we have been looking at this sustainability along three main areas. So in addition to environmental sustainability, also social sustainability, so including, for example, trustworthiness and inclusion, as well as economic sustainability. If it doesn't make sense economically, it is not possible to realize it. Already referred in the very beginning, this duality, sustainable 6G, so 6G itself needs to be sustainable, and 6G for sustainability, helping other sectors of society to be sustainable. And we are having a loop of activities around this principle. We are analyzing stakeholders, ecosystem models, gathering feedback from society, defining use case requirements, and having these different items interact each other. Based on this, we have come up with this set of use case families that are in the circles in the center. Around them in the boxes, the different use cases. On top of each of box, the so-called representative use case representing this use case family. And this was also, for example, widely discussed last year spring at the 3GPP event, and has had quite some impact in this 3GPP use case work. So then about the sustainability analysis. We have the use cases that have been defined based on human or planetary goals, or in suboptimal case, the use case have been defined by other means, impacting then our understanding on the human and planetary goals. Based on this, we have created descriptions of the use cases, looking at what the problems need to be solved to realize the use cases. So answering also why do we then need 6G, and then started sustainability analysis, looking at the technical side, technical requirements, looking at the business aspects, and then the actual sustainability evaluation along these three axes: environmental, social, economic. In the sustainability evaluation, we have been refining so-called key value indicators. So if it is not straightforward to come up with the key performance indicators, but we need to approach it if the challenge is not so easily to be put in key performance indicator format, so then we have created first so-called key values. Based on that, we have been then moving forward and analyzing the sustainability impact of the handprints and footprints and other dimensions. And from these key values, then we have been trying to map those into key value indicators that would be easier to measure. And sometimes those can be mapped then forward all the way to key performance indicators, but sometimes they remain as use case or enabler key value indicators. And then when one would continue this analysis further, one could then recognize that what kind of additional needs there might be, or if one would need some refinement on this overall work. Then, if getting this more concrete via an example, we could take as an example use case this cooperating mobile robots. And in this case, so we are looking at robots that communicate locally to perform tasks beyond their individual capabilities. And here problems to be solved include, for example, then how to use the limited resources efficiently, and how to have safe and trustworthy interactions with the tools that can make decisions. Why 6G is needed here? So even though 5G release by release is improving this front, there are also cases where we need improvement in terms of latency, reliability, scalability requirements, and so on. Additional reasons why we need 6G can be seen here. This we have then been mapping as much as possible into key performance indicators, showing that mostly in these cases there is not so high mobility, there is requirements for high reliability and so on. Then we have been looking at these human and planetary goals. How are they coming in these different areas of sustainability, and how are we mapping this to the United Nations Sustainable Development Goals? And then here you can see then examples of these key values. For example, handprint benefit, environmental sustainability key value is to increase efficiency in production processes. And here then, in terms of these key values, we have been looking at key values that represent the impact of the use case and technology, and also such that are measuring these enablers. And then we have been mapping these key values to the different indicators. For example, on this resource efficiency, the amount of raw materials per materials used in products. And then further creating this overall mapping and recognizing if we are talking about use case key value indicators or enabler key value indicators. And the further results and analysis of these cases we are about to release in the final work package 1 deliverable coming out in the early days of May. One other significant track where there is finalization of the work ongoing is in this end-to-end system view that I'll say a couple of additional words. So here we have been looking at the architectural design principles needed and have created 10 main principles, from support and exposure of 6G services and capabilities, full automation and optimization, flexibility, scalability, resilience, availability, persistent security and privacy, having the internal interfaces cloud optimized, separation of concerns of network functions, network simplification, and minimizing the environmental footprint and enabling sustainable networks. Based on these principles and based on our material, lots of additional analysis, we have come up with this all the time updated overarching 6G system blueprints. And here you can see the latest version where at the lower part we have the infrastructure layer with the cloud continuum extending all the way to the devices. On top of this, the network functions layer containing also the new beyond communication functions, for example, related to sensing or AI as a service. And then on the top, we are serving then the applications in the application layer. And in between this, we have still the application enablement platform layer, making it easier to create these applications via application programming interfaces and aggregation. Besides of this, we have the pervasive functionalities with, for example, management orchestration, security, privacy, and resilience, data management framework, and the AI framework. And the latest results from HexaX2 you can find from our website. So on this track of D1.deliverables, the final deliverable with analysis related to my speech coming early May. And then from this work package 2, final deliverables on this end-to-end system view coming also then and as well as early July. Whereas then the technical work packages have already recently released their final deliverables, for example, on the architectural framework, on the radio solutions, enabling technologies, devices, and infrastructure, as well as smart network management framework. You can also via our website find presentations and videos, and then the final demonstrations are released at the EU CNC and 6G Summit this year, June, in Poland. So that concludes my presentation. Thank you.
Thank you very much, Mr. Mikko from Finland, giving us a wonderful sharing. Next, I'd like to give the floor to the Professor Li Yonghui from the University of Sydney, Australia. He's going to share with us how we combine the 6G sustainable green 6G with sustainability. He's gonna give the speech from Zoom, so let's switch to his. Hello, can you hear me? Okay, we are ready. You can share if you are ready.
The conference for the invitation. My talk today is a green cell-free massive MIMO on optimization embedded deep reinforcement learning approach. Without 6G, integrate a set of advanced technologies to create a highly connected, efficient, and intelligent urban system. So in this talk, I will explain how our work built on this foundation mainly focus on the cell-free massive MIMO system to address the energy efficiency through some optimization techniques. The cell-free massive MIMO is advanced distributed communication architecture to overcome the limitation of a traditional cellular network. We know the current cellular network are interference-limited system, where cell boundaries are predefined. So this creates the intercell interference, which limits the system performance. Also, the spatial efficiency decreases as the users compete for resources within the cell. So normally, the users at the cell edge has a very poor performance, has a poor coverage and strong interference. This will result in a poor user experience and uneven quality of service. So cell-free massive MIMO address these challenges by removing these fixed cell boundaries. In cell-free massive MIMO, multiple APs cooperatively serve all the user equipments, or we call the UEs in the network. And APs are coordinated through a centralized processing unit, which optimizes resource allocations and minimize the interference by leveraging the channel conditions. So this approach brings great benefits, including the removing of the intercell interference, improve the spatial efficiency, and also uniform quality of service for all users. This also enhances the coverage for edge users and reduces the overall power consumption. So in summary, cell-free massive MIMO not only addresses the critical limitation of the traditional architecture, but also sets a foundation for a robust and efficient communication system in 5G and beyond. Cell-free is great technologies. You can see offer many benefits. It's also can greatly improve the user experience. However, this also faces several challenges. The most big challenge is energy consumptions. Its energy efficiency remains a big concern. Energy consumption grows linearly with the number of APs. Antennas and the user equipment are served by the APs. Basically, we have the number of users and number of antennas, number of access point increases, so energy consumption will increase linearly. So these high energy demands will greatly increase the operational costs, also has a significant impact on the environments. So the main contributor for energy consumption are the transmission power, signal processing power at the APs and the CPU, also the front haul energy for data exchange. So power allocation and access point selection are the key strategies to address these challenges. By effectively and efficiently allocate powers and activate which APs is activating, which APs is in the sleeping mode. So by intelligent and optimally optimize these variables, we can greatly reduce energy consumption without compromising the performance. However, optimizing this factor is challenging due to the non-convex nature of the problem. Also, as the network scales, when the number of APs, number of users increase, the computational complexity of the optimization also grows, make it essential. So it's very essential to develop some scalable and efficient solutions. So the key objective for our work is to develop energy efficient strategies for cell-free massive MIMO systems. So we want the system to be scalable. Whenever network changes or network size increases, so we don't need to redesign, re-optimize our framework. Once our work is designed, is optimized, our work one fits all. When the network changes, dynamic changes, we don't need to re-optimize our solutions. So we focus on the dynamically optimize the power allocation and AP selection while maintaining quality of service. So this is very critical for the 5G green networks to address the growing demands in IoT in the urban environments. This is our system model. We consider the cell-free massive MIMO consists of multiple distributed access points connected to the central CPU via front haul links. Each AP dynamically serves multiple UEs using multiple antennas. The energy model accounts for the transmission power, hardware consumptions, the front haul power consumption components, also incorporating active and sleep mode to optimize the energy usage. Our key contribution is the joint optimization, the power allocation, and the AP selection to ensure both the energy efficiency and the scalability. So here, this is the problem formulations. We aim to minimize energy consumption in cell-free massive MIMO while ensure the quality of service requirements. So you can see this is the objective functions. The key power consumptions include the 3 parts. The first is the power consumption of activated APs. Second is the front haul energy cost. The third one is transmission power for all the AP and the UNI connections. Now, there are 2 constraints. First, the minimum data rate for each user. The second is the total power consumption of all the APs and the UEs. Also, we count for the strong correlation between the activated AP and the power control coefficients. So optimize this cell-free massive MIMO system is very, very challenging because it is a non-convex problem. We call the mixed integer and the nonlinear programming. It's non-convex problem. It's very difficult. Traditional optimization methods are very computationally intensive and unsuitable for real-time decision making. Also, conventional methods, we need to resolve the problem whenever system size or wireless channel condition changes. This also makes it very impractical for the practical applications. As network size increases, these methods also faces some significant scalability issues. So our solution, we call the optimization embedded deep reinforcement learning, or we call the OSACG in short. We integrate optimization techniques with the deep reinforcement learning to address these challenges. The key advantage is offers real-time, can real-time adapt to the dynamics, can also efficiently handle the dynamic changes in the wireless channels. Our proposed scheme is scalable to the network of various sizes, also reduce the computational overhead in traditional methods. It's a balanced energy efficiency and quality of service requirements, and provides a robust framework applicable to other optimization tasks. So this is the basic the workflow. We use a deep reinforcement learning. Deep reinforcement first does the online offline trainings. Once it is trained, we use the trained model to do the online inference. This enables real-time optimizations. And the data is first pre-processed. Then we have a successful approximation module to refine the solutions. We using some of the linear approximation to simplify the original non-convex optimization problems. Then we have this graph actor critical network is used to decision makings. So these components collectively ensures efficient and adaptive optimization in real-world scenarios. So there are 3 inputs to the model. The first input is the system states. System states like large-scale channel fadings, channel estimation states, and the AP-UE association information. That is which AP serves which UE. Second input is action space, which is the power allocation levels for active APs, selection for active or sleep modes. Third one is the constraints, the minimum data rate requirements for users and the total power constraints for the network. Then we have 2 outputs. The first output is the power allocation decisions. What will be the optimum power levels for active AP. Second is AP selection decisions. Determine which AP remain active, which one enters the sleep mode. So there are 3 states in the network. First state is the current network states, including normalized the large-scale fading parameters, channels, state information, active AP status. Second state is the historical states. That's the previous configuration of AP activities and the power allocations. So this is combined with the previous states with the current state to create a holistic representation for decision making. The third state is the policy states. That's the internal state of actor critical network. We have actor states which determines optimal actions based on the current observations. Then we have a critical states, critical states, which evaluates the reward associated with the actions to improve the future decisions. So pre-processing module basically to ensure the stability is mainly to normalize the large-scale fadings and also integrate the past and the current data, allowing the model to make the more informed decision. Successful approximation module is, as I mentioned before, is the key objective to simplify the complex optimization problem by breaking into the manageable steps. Basically, we first replace the non-convex terms with the first order Taylor expansions. We then iteratively update the approximation. Then to solve the mixed integer and the linear programming problem, we first transform the mixed integer variables into the continuous one because you can't directly optimize the integers in the machine learnings because it's non-differentiable. So we first transform the mixed integer variables into the continuous one. Then we use the first order approximation to achieve the feasible solution. Then we quantize these continuous variables into the integers. So the graph actor critical modules built on the graph representation of the AP-UE relationship. We use a graph to capture the relationship between the AP and the UEs, their connections. Then we use a graph transform network with multiple height attention to prioritize important interactions. The actor critical mechanism refines decisions over time for stable and improved outcomes. So these slides explain how the actor critical modules is used in our framework. On the left, we have the actor modules, which leverage a graph transform network to process the state representations. On the right, we have the critical modules, which use multiple fully connected layers and embedded layers to evaluate the quality of service, quality of the actor action states. So the graph transform network is essential to capture the complex relationship and the dependence between the nodes in the network and also enable the robust decision makings. The beauty of a graph transform network is it's scalable. It's basically, it characterizes the complex relationship and the dependency between the nodes in the network. So the network size and topology changes, you don't need to retrain the models. It also adapts to the changes in the network. For example, when the dynamic of AP activations, user mobilities, or the channel condition changes, you don't need to retrain the models. And the reward function is designed to get the dialog framework to minimize energy consumptions. Also, we incorporate the quality of service and the power consumption to balance the energy efficiency with the performance. So in this figure, we compare the average power consumption of the 4 schemes under 3 different scenarios. So in figure A, the y-axis is the power consumption. Axis is the different number of UEs. You can see as the number of UE K increases, the average optimal power consumption also increases. The performance of our proposed scheme, this is the second bottom line, which is it's close to the ISAM. ISAM is the bottom one. It's the optimum one. We can see also greatly much better than the conventional other optimization schemes. So in figure B, we compare these schemes for different quality of service requirements. ENTA. So ENTA is quality of service requirement. That's the minimum data rate requirement for UEs. So we can see that as the minimum data rate requirement increases, average optimized power consumption also increases. So the relative performance of this scheme is similar to the figure A. So this shows our schemes can greatly reduce the power consumption. And all this shows the convergence. You can see our schemes converges very quickly. Our other conventional DRL scheme doesn't converge. The dashed line shows the conventional DRL scheme. Conventional deep reinforced learning schemes. We consider this soft actor critical SAC scheme. You can see it doesn't converge because as the network sizes increases, the number of variables and the complexity will increase. So SAC doesn't converge, cannot handle this complexity. So due to time limitation, I just quickly go through the slides. This shows how our scheme can be generalized, generalization capabilities. We trained the model for a number of users, k equal to 40s. then we directly apply this for online interference for k equal to 40 to 50. So you can see the feasibility ratios. That is the probability that our models satisfy the constraints. This only changes slightly as the k changes. So this demonstrates outstanding model generalization capability of our proposed model. So in conclusions, our work, we achieved great energy efficiency, also scalable with real network scenarios when the network size and channel condition changes. So by combining the deep reinforcement learning with optimizations, our work sets foundation for future wireless system. Thank you very much.
Thank you very much, Professor Li, for your presentation on AI plus AI communication. Next, I'm going to give the floor to Mr. Xiao Yong from Huazhong Science and University to bring us the presentation on the latest research report on network plus AI. It's a great privilege to report to you the work we have done on net carbon zero and emissions and AI for 6G and beyond. So this is my outline. Just now, Mr. Gong has made a very comprehensive presentation. So as we integrate AI with network, there are a number of challenges. The first one being the boom of traffic, and also the power consumption would be getting much higher than before. And second, there will be a problem. As the traffic gets more higher, we don't know what is the specific reason. Whether it's brought by AI, it seems that the broader the bandwidth is, there would be, or the ratio of a channel. So the higher the energy power consumption, the higher the traffic is. Now with the AI computing power, there are more issues because as the skin of the power consumption is getting unclear. So like DeepSeek has revolutionized our awareness. So the many reasons could be the traffic or the power consumption. So it is not a simple relationship. So right now, our study and research is still in the preliminary stage, especially as we incorporate communication with computing, and we are not clear what is the power consumption and communication. Secondly, for AI, we have a lot of AI options right now, and the explainability for AI is quite broad, and it's very hard to calculate the different AI algorithm or energy consumption and the impact of different factors to our task. And right now, it is very hard to identify the reasons behind. It is different from the traditional communication network. The conventional network is guided by a mathematical model, but right now it's very hard to get a specific energy consumption through a clear mathematical model or formula. And so the reason remains unclear. With the same algorithm, the performance is very different in the different scenarios. And right now we have many narrow AI or broad AI. And so in the same AI, in different tasks, the performance is different. So what is intelligence? And how do we identify and measure what's the power consumption of the resources? The relationship remains unclear. So the high resources and the relation with the high energy consumption remains quite unclear. This is a target that we're going to research. And given the very high ICT energy consumption, now the three main operators, like our Huawei Center, we have deployed the LLM. Once they are getting deployed, the energy consumption will be soaring above the roof. And right now, we are already talking about using nuclear power to train AI LLM. So if every enterprise, every operator use LLM, then we will need to build every nuclear power, and it's not good for the sustainable development goals. So we have done some research study in this area. First, from the explainability, the awareness of the network. For the CO2 concentration, it is not very easy to control. And second is the low carbon, and we're talking about the CO2 concentration, CO2 carbon by different AI computing power and distributed algorithm. And so it's not necessary for every operator to train a model or turn it into the agents. So once we train one model, it will be available for many other operators to use it. So we have to have a mindset shift. We can unify the agent model in the one framework, and we can expose or have exposure of the capability of every agent, and we can just schedule it. There's no need for the repeated training for the tasks. So these are our main works in three ways. First is the distributed AI and the energy consumption. We have tried to develop a model to identify the energy consumption of AI computing power. So we have established a mathematical framework. And also the performance and energy consumption, we want to make a math model. And this is the platform that we have built in our lab, but it has many interesting observations. There are 6. It is a small system of distributed network, and every unit is connected with the small box that can detect and test their real-time energy consumption. So the y-axis is the time, and we have the energy consumption axis. And so we have a very clear AI model and a rule. We have 4 stages. The first stage is the local load to the cache, and the second stage is to send for coordination, and third stage is computing stage. You can see many points. That means approach. So how many approach refers to the points.
So you can see these 4 stages, and you can see the pattern in many of our GPUs. So with this pattern, you know how many pods you train, and then you will know the size of the parameters for transmission, and so you can actually observe that very clearly. So with this, we can establish a mathematical formula. So we can actually pinpoint or have a very accurate records of those data. And you can see actually after this mathematical modeling, we can always observe this kind of pattern. You can see here as well. If you say the precision is 90%, and then within 10 rounds or 20 rounds of training, then you can reach 90%. But if you want to reach 95 or 99%, so you can always follow this kind of pattern, because the tailing effect is very strong, right? If you want to reach 80 or 90% accuracy, the cost is not very high, but like 95 or 99%, then the cost can be very high, right? Because now many AI models said that when they improved the accuracy by 1.1%, and then they will probably publish a paper. But actually, the cost is very much if you go beyond the 90%. But if you reduce the accuracy a little bit, then you can reduce the cost or energy consumption a lot. So it doesn't. We've been thinking probably not all AI applications or tasks need such higher precision. If it's only 80 or 90% of accuracy, the cost is not high. If you always want to reach 99 or 98%, the cost will always be high. So if you only want to reach 80 or 90% of accuracy, the cost is not high. So that's what we want to build in terms of the model. And you can see this is the curve, our mathematical model. And you can see our model is a little bit drifted from the very accurate one, but it can still give us a lot of good results. So you can see we can still have very good result. So what's the advantage of this kind of model? So I think you can first of all determine what's the accuracy you want, like 80%. Then we can calculate the collaborative training on the edge, and then you don't have to list all the parameters here. You don't have to exhaust all the parameters here. Probably with optimal parameters, you only need to train like 10 rounds or 20 rounds, and then it can give you an optimal solution. And also, we have done a lot of other works in terms of power consumption. We found that there's a connection between the servers and also energy consumption. So we've been thinking, do we need a server every time? So in the distributed computation system, the data is actually in local, right? But in the past, you upload to the cloud and then you do the centralized computation. But with distributed computation, the computation is localized. But do we need all the data for local computation? For example, Wuhan's data is very similar to Huangang's data. Do we need to recalculate the data in Wuhan and also Huanggang 2 times? So probably we can only compute those data with personalized features or individualized features. And for those with big contribution, we do the computation. If it's very low contribution, you don't do the computation, right? For example, when it has the same contribution, you can still have further evaluation in terms about the carbon emissions, things like that. Of course, there's a differences between the energy consumption and carbon emission. So we have some evaluation indicators at different nodes, and also things like a contribution. Second, when there is a same contribution, then we will prefer the lower carbon emission. So in this way, you can actually drop equipment, right? It can save your time and also energy consumption. And so that's a very efficient way to reduce our expenses. So we compare the equipment dropping and the non-equipment dropping, and we found that our solution of dropping is actually still very good. And you can see on the right side, there are different energy consumption brought up by different parameters. And also, we integrate the different minimal parameters with the equipment dropping. And for example, with this, you can get to the best arrangement or solution. So now we know there is a DeepSeek, and it contributes to one point, which is load balancing. That is the balance between the communication and computation. So DeepSeek can reduce our cost very well. Why? Because it uses as much as computation volume. So it can actually have a very full arrangement of the resources for computation and communication. But in the past, the distributed network, everything is synchronized. So you have to finish the first round, and then you wait for the finish of the first round, and then you continue with the next round. But now we have asynchronized collaboration, so you can have a faster speed and you don't have to wait for the previous rounds to finish. So it saves your time and also reduce carbon emission. And also here we did some model optimization by using our theory. So I would not dwell on that. And what we do very good is the fitting. So we collected the data and then we come up with the procedures, and then we found it's very good result. And also with the asynchronous collaboration, we found sometimes it's very difficult to converge, right? For example, when it has very high confidence level, it has a very bad result. So here we mentioned we can have some adjustment. For example, we can distribute the data or optimize somewhere, and then you can we optimize, for example, every round. So, and also with the asynchronous collaboration, it can help us to achieve the accuracy we want. Okay, so you can see with our theory, it can reduce the energy consumption and also the training time. And here I like to talk about the low carbon design. So there's different carbon emission in different power grid, and we studied the US power grid, and because they opened the data to us, right? So we come up with this modeling, and we study the correlation between the carbon emission and the power consumption, and we studied different regions in US over the past 20 years, and you can see there are always very big changes or differences. And for example, the carbon emission of today will be very much different from the past. So there is the impact from the time and also space, right? So, and also during the year, you also have different carbon emission or power consumption. For example, the emission will be different during the day and the night, and during the summer and the winter. And so there this kind of temporal impact. So if we can establish this model or model the modeling have very good modeling, we can understand what's the best time to use the power, right? So we come up with the life cycle modeling using for the AI algorithm. So with this modeling, we can decide on what stage and where we can have better optimization of the power consumption and also carbon emission, right? So that is a life cycle concept. We come up with 4 life cycle stages, and we found that the model deployment and training has the biggest carbon emission or power consumption. And so during this stage, we can actually, for example, have a distribution, or we can have optimization. Lastly, we come up with the DETA data. So we can actually have a dynamic energy trading between different regions. And the second is dynamic task allocation. That means we can put some of the high energy consumption tasks in some low carbon emission area. So we combine these 2 concepts. We call it DETA, DETA, dynamic energy trading, and the task allocation. So it can help us to reduce the carbon emission. So you can see a very significant reduction in that sense. Especially if you can utilize the time advantage, and then you can actually reduce the carbon emission even when there is the same energy consumption. And especially in the distributed scenarios, you have a very good solution, very good result. Lastly, I'd like to talk a little bit about our mobile digital intelligent agent communication system. So recently we published a paper talking about the mobile agent communication network. So we used the paper to solve several questions. First, the development of infrastructure. You know, there's a match between the infrastructure and the traffic. In the past, every 10 years, we update the telecommunication network, right? But AI's energy consumption keep increasing, right? So we need to have digital intelligent agent to collaborate. So, for example, the AI native and intelligence network, things like that. So every day we will have different energy consumption and different demand. Probably next day we will have a new AI model. So there's a very fast speed of update of the network, and every day there will be different user demand. For example, tomorrow you will have a new TikTok business. but probably you design the network for the past demands instead of a new demands, then it will lead to the fast increase of the carbon emission. So we come up with this concept of mobile agent information communication network. So we published the paper, and in the 6G, we've mentioned 3 transformations. In the past, we need to be goal-driven. In the past, it's all about data transmission, but now it will be goal-driven in terms of the data transmission. Second is, in the past, it's a centralized management or governance, but now it's autonomous and distributed management and control. Third is the continuous evolution instead of 10 years of evolution, right? So every day you have evolution. So finally, we come up with a vision for the future. It's kind of like a hardware platform, and then you can see we design different agents to solve different interactive solutions or tasks. And so as long as you design into intelligent agent, as long as there's a same tasks, you can always call the model to use, right? So this is the net AI in net system. So there are a lot of small intelligent agent modules, and in every module you see the neural layer, and you can have random or optimized arrangement or combination, and it can target at different tasks. So that means you don't have to train the network every time. You can always use the old model for new use. So that's all from my side. Thank you. Thank you very much, Mr. Xiao, for providing a lot of more information in the intelligent agent and also 6G, sustainable green 6G. Now I'd like to give to the Mr. Zhou Shen, Associate Professor, Department of Electronic Engineering, Tsinghua University, to share with us.
Because my slides was prepared, I was told I have to prepare the slides in English, so I had better introduce our work in English. Okay, and okay, so this is our recent work on green wireless networking with the integration of communications and AI, and so this is the outline of my talk today, and so I will briefly review what we have done in the past maybe 10 years. Towards the green wireless communications in 2 ways. One is how do we use AI to enable green wireless communications, and on the other hand, what is the role of communications that we can achieve green AIs? And I will also discuss some actually it's ongoing work in our group, and then I will summarize. So this, and for 5G and beyond, there is a common sense that, like in 6G, we're going to achieve connected intelligence for our digital life, and there are many applications. And but as we already know that the energy consumption of our cellular network is a big concern, especially for 5G. And its energy consumption is much larger than the 4G base station. And there's a traffic explosion and also the related energy consumption. So this is not a sustainable growth path. So we're going to seek for new opportunities. And on the other hand, this is a very hot topic regarding the AI. So actually AI is nowadays, with the development of large models, as we can see from here, especially for the language models, the size of the model increases dramatically, and also the energy consumption in terms of the carbon emission of training those AI models also increases substantially. So this is what we call this red AI. So how do we transform this red AI into green AI? Basically, the term green AI refers to the AI research that uses novel research results while taking into account the computation cost. So now we know that there's a data showing that performing an image generation task, it actually consumes energy consumption 1,000 times larger as a similar energy as running a laptop for like 20 hours. So this is a huge amount of energy consumption. So as a wireless communication researcher, how do we address this issue? So there are many issues, but some of them is not our advantage, is not our major. Okay, so therefore there are something that we can do is like power management, and how do we utilize renewable energy and the mobile device and edge device coordination. So basically there are two ways to do that. Actually, we're looking at the AI and communications. So first of all, we can utilize AI models to save the energy of wireless communication devices. So basically, this comes to the, of course, we've been looking at these issues ever since 2018, and we can use reinforcement learning to also, later we can use like LSTM to predict the future traffic so that we can control the base station, the energy consumption of the base station, and basically that is resource allocation accordingly. So this is our previous work. But utilizing AI in terms of optimizing the wireless communication networks also faces like substantial increases in the AI itself. In order to perform those AI models, you have to acquire data, and also you should train the model, as well as of course you are also going to do the inference on the go. So therefore, utilizing AI in optimizing wireless network, you should compare. You should, in the first place, you should judge the energy consumption in communications, the savings in that, and also probably sometimes if the energy consumption in AI itself is larger than the savings, so this might not be a good business, right? So this should be reconsidered. This is one thing. But the other thing is that how does wireless communications can enable green AI? So this is our recent effort. So actually, Professor Xiu just mentioned we can. So a very good example of utilizing AI through wireless communications is federated learning. So basically, if you look at the federated learning, it's not very energy efficient. So how do we achieve better energy efficiency for federated learning? So here we can, of course, we have done some work in terms of optimization the convergence speed of federated learning under the constraint of the total training latency and limited communication bandwidth. But here, our contribution is that previously, the research on federated learning only look at those convergence speed in terms of epochs, but we look at the real latency in terms of seconds. So therefore, we can, our work with respect, comparing to the benchmarks, our work can achieve better test accuracy for a given time. Also, in terms of energy, so our setting is that initially we have some energy, but we look at the remaining energy after certain rounds of training. So our proposed algorithm can still have more energy in the battery. So that means our algorithm has better energy efficiency. So this is our work on federated learning. Of course, there's another issue that people often talk about is how do we save the device energy? Because nowadays our devices are running a huge amount of AI apps. So therefore, your battery actually drain very rapidly. So, so one way is that we can offload the computation tasks on our cellular phones or on our devices to the edge server. Basically, the communication offloading actually is a classic problem, but nowadays there's a new thing is that in the cloud and also in edge server, people are using GPUs. So that is very different from the CPU architecture. So there's an advantage of parallel processing or batch processing of many tasks. So how do we utilize this batch processing capability on the edge so that we can save more energy on the mobile device? So therefore, we have done some work. This is quite very theoretical work, but anyway, so we are trying to save the trade-off between average power consumption on the devices with respect to the average computation time via a very solid Markov decision process analysis on the algorithm. So basically, as we can see, that our algorithm can achieve a Pareto optimality on the trade-off curve between the energy consumption and the latency. Okay, so you can according to your requirements, depending on the latency that you need, you can just achieve the best energy consumption on the mobile devices. So moreover, we also find actually you don't have to achieve if you have better data, so in terms of inference, if you have better data, for example, for autonomous driving, in autonomous driving you have to environment perception. But if you have a good view, you can find the object in the view with less computation if your deep neural network has the early exit capability. But this happens for many deep neural networks. So then we come up with an idea that, okay, so if we to try to understand the environment on a single view will require longer computation as well as larger amount of energy consumption. But if we can utilize the view from other vehicles so that we can do collaborative perception, surprisingly we find that, okay, because we have more views, so that we have enhanced understanding of, we have sufficient information for the same environment, and we actually can come up with satisfactory precision with early exit. So that is basically, but the cost is that you have to transmit the view from other vehicle to you. So basically you trade off communication, the energy consumption from communication to the savings of computation energy. So this sounds very practical, but we have done some experiment, and we find that actually the gain is surprising. That so the constraint is that under the same detection performance, our algorithm, so collaborative perception, you get data from other vehicle, actually can save 40% of computation energy on board, okay, compared to the other things. So this is very important because for the environment perception on the electric vehicles, actually, this is a major portion of energy consumption for the intelligent driving component on EVs. So this is also very important. So for the future, we are looking at the deep integration of communications and AI. So that goes beyond our previously discussions on how does AI can enable green communications and vice versa. So now people are talking about native AI. So like AI as a task. Also AI as an enabling technology. So many things is going on. But for native AI, so people are looking at how do we design and select lightweight AI models, like small models, even though nowadays everybody is talking about big models, large models, okay? And for the, but our focus is tightly coupling communication and computing networks. So we are trying to optimize this task scheduling by fully utilizing the temporal and spatial resources with priority on energy sustainability. So I just provide some examples of our recent work. First, for the task offloading I have just mentioned, but we can do better job in terms of rather than offload the whole task to the edge server, we can actually tune the model, and we can split the model and offload part of the model to the edge server, because if you initially you transmit the raw data, that probably will consume huge amount of energy consumption in terms of communication. But if you transmit some intermediate result, you can save the communication load as well as your computation energy consumption on the device. So we come up with some online partitioning algorithm, and we can achieve a substantial energy consumption reduction. Also, as I just said, for the edge server, many edge servers now are utilizing GPU. So considering there are parallel computation capabilities, so we can use, we can utilize, for example, we can consider multiple users that by splitting optimization, so we can allow multiple users, but if they are running the same deep neural network, how do we utilize the parallel computation capability on the edge server? So that will bring up a new problem, that how do we do joint deep neural network splitting on multiple devices, but that you should also take into account the wireless communication resource allocation as well as the parallel computation scheduling on the edge server. So we also have developed some algorithms over there, and we also show that this is actually considering the parallel computation capability. When we design this task splitting, we can save a huge amount of energy consumption. So this haven't been addressed by recent current works. Moving on one step ahead, so that not only the edge server are using GPU. So nowadays, even our cell phone and our laptops, they also are equipped with hybrid computation architecture. So that means we also have GPUs on board. But previously, when we address the energy consumption on the devices, we use this CPU-oriented energy consumption model. But via our real testbed simulations experiments, we find that current CPU-oriented energy consumption model doesn't fit. So actually, we come up with a new energy consumption model that's fit for GPUs as well as hybrid architectures, so that we utilize this model to revisit our offloading algorithms, and we find that with better understanding of the energy consumption model on the mobile devices, we can achieve better algorithm for the task offloading. Okay, so due to the time limitation, I just come to our conclusion. So now, from our point of view, so the opportunities of like green, intelligent, and interconnected 6G network, for example, we require more flexibility and more efficiency and greener wireless communications as well as computing. But there are some opportunities. So therefore, we can come up with some future directions, like how do we leverage the characteristics of computation tasks, especially AI tasks, to better tune not only the wireless resource allocation, but also the communication task scheduling. And of course, you have to do accordingly the resource allocation optimization. And also, you can utilize the device mobility. So this is also our we recently find that the mobility of devices like vehicles and mobile devices can actually provide you opportunities for energy saving. So that is also was investigating. And also, the influence of large models like DeepSeek and GPT-4 recently. So if we have this model, of course, the first insight is that, okay, we have such huge models, our transmission and computation energy consumption will blow up. But on the other hand, it seems that many contents can be generated locally. So probably we don't have to transmit those amount of information. So this comes to the area like semantic communications, but we might look at the energy consumption of those issues. Okay, so that's all for my talk. Thank you very much.
好，谢谢。
Thank you very much, Mr. Zhou, for giving us a brilliant sharing. Now I'd like to invite next speaker, the Deputy Director of China Mobile R&D Center for Networking, Planning and Optimization, Mr. Gao Feng. So he's going to give us a presentation from the perspective of operator. Dear guests, experts, good morning. So I'm going to use Chinese to do the presentation. My topic is building sustainable green communication networks. First of all, I'd like to give you the research background. So you can see actually in Europe, in China, and also in United States and Japan, there are the carbon emission or neutrality goals set up. And also in China, the Information and the Industrial Administration also have come up with the requirement for low carbon or carbon neutrality. For example, in 2021, China Mobile has also launched the 3 energy and the 6 green dual carbon actions. So it's about green energy, clean energy, and also AI enablement. And 6 green refers to the green network, green energy, green energy efficiency, green supply chain, and also green office and the green culture, green enablement. So those are the 6 greens by China Mobile. From 4G to 5G, we see the 5G energy consumption has been increased by 2 to 3 times, or probably higher than that compared with the 4G. And also the wireless devices accounted for 70% of the total consumption. When we are moving towards 6G, probably we're going to use millimeter wave and also the terahertz. And we hope that the 6G energy consumption probably will be 10 times higher than the 5G. So that's going to be a big energy consumption challenge for all of us. Now I'd like to give you some information about the work we have done in the dual carbon goal. So as you know that the income of China Mobile has surpassed more than 1 trillion RMB. The profit has been over 30 billion RMB. But in 2024 alone, we have about like 40 billion power bill. So you can see that's why we that has taken out from our revenue a lot, so leading to a relatively low net profit for us. So we have done some work in terms of green power or energy consumption. So I'd like to give you some more information. We have done a lot, for example, in 3 dimensions. First, information transmission. We have a lot of evaluation work done. So you can see the transmission accounted for about 70% of our total energy consumption. You can see, especially we have done the evaluation target on the BBU and the AAU. The unit. So we study the transmission quality and efficiency with the per every energy efficiency loss. Second, we had the green evaluation of the information processing. We evaluate the energy efficiency of information processing for high-performance computing equipment such as servers. The third evaluation is done on the information infrastructure. For example, POE method in evaluation has been adopted. So the total data center energy consumption is compared against wireless equipment energy consumption. We require the ratio should be less than 1.5. In terms of the green network construction, we come up with the evolution from DRAM to CRAM. We want to come up with minimal network, intelligent minimal network. So we develop the integrated energy cabinet in the DRAM. dimension. So as to save the energy, the cabinet has been deployed across 31 provinces with 35,000 units installed. It can save about 20 million kilowatt hour per year, have a very big carbon reduction. And also, we have adopted the ultra-compact basic station that can help us reduce power consumption by 30%. And also, we have adopted the multi-equipment integration, so can save the space by 60% and power consumption down by 30%. And also, we have adopted liquid-cooled cabinet. It can reduce our power consumption by 15%, and also the data center POE will be dropped by 0.2 to 0.3. In terms of the green operation, we have also done a lot of work. We focus on different dimensions, including the temporal and spatial domain, and also frequency domain to save energy. For example, in terms of the carrier and off, or it has been shut off, or the channel has been shut off, or we have very better control of the idle power. And we also carried out a very interesting experiment. For example, we found there's a quickly increase of the energy consumption after we deploy the 5G. So we have carried out intelligent power control or adjustment. And also, we study the measures taken by the operators and also our partners. We found that they just shut down many switches or hardwares. I've been to a southeastern province in China. One of our partners has more than 5,000 basic stations. And during the night, they said they just turn off the 5G base station completely due to the high energy consumption. We also have done an experiment in the northeastern province in China. So we shut down the idle channels, and we make a comparison of the traffic, and you can see the cost. So in this way, it can save a little bit more of energy consumption, but actually, it still didn't give us a very big advantage in terms of the energy saving cost. So we've been thinking, how can we maintain the energy efficiency or improve the cost? So we've been thinking, how can we maintain the energy efficiency or improve the efficiency and at the same time balance the cost? In terms of the green maintenance, we also have done a lot of work. We built up a integrated system through the modeling and also evaluation and uniform the O&M. We can achieve a green maintenance. So we come up with this green and low carbon product system, which we call it 1+1 green and low carbon GLC operational framework. So this is an integrated energy saving platform for us. So it provides a one-stop solution. The method we adopted is 3 layers and dual domain. So what are the 3 layers? You can see on the group level, we have a layer. So it's an integrated platform for energy consumption management. The second layer is provincial or prefecture level, county level platform. And the third level is a park or building specific or basic station level. And the 2 domains refers to the management domains and also the operation and the control domain. So that's the overall framework we established. And this is a AI-assisted GLC MNC platform. So this is a video. I'm not sure it can be played or not. So anyone can help me play this video? Because someone needs to click the button. So as you can see here, on our management and control platform, MNC platform, we introduced the DeepSeek. So we came up with this intelligent agent. It can help us achieve two targets. One, it can give us intelligent Q&A and display. You can see it gives you this dashboard automatically, so it can showcase the energy consumption situation in different regions or provinces. So you can see it can also provide some tools or functions to our regional companies or provincial companies or to our partners in the regional province. So it's kind of like a digital agent or assistant. Second scenario is it provides an evaluation tool to us. So it gives us multidimensional analysis. Through this analysis, we can help the province or regions to give them a score in terms of the green carbon. And so the score is kind of like a scoring system. So it also gives you the reasons for that score. In this way, it can help contribute the low carbon management in those regions or province. So those are the work we have done in terms of the green development. And talking about 6G green network work, according to TMF, the 6G development or green development needs to evolve from the judgment made by experts to the end-to-end automation or intelligence. So it needs to be a full process and closed loop. So it involves like data collection, intelligent collection, and also intelligent prediction, and also automatic generation of strategy, and also distribution of the strategy, and also the feedback from the closed loop, and also dynamic optimization. Those are the works we need to do further to make a breakthroughs. And also, we need to achieve those goals by improving the technology strategy and also by using the AI for better enablement. Also, we need to have, for example, new breakthroughs in the terminal and also in the base station. Also, the activation of the many things, for example, and also like the enablement of the AI, digital twin, and also intelligence native, and also integrate sensing, collaboration. So with all those kind of technologies, we can achieve 6G green network development. And for China Mobile, we focus on the energy use, the energy supply, and energy evaluation to develop our green network. In terms of energy use or energy consumption, we have done a lot of technological research. We hope we can use high-efficient transmission and high-efficient distribution technology. In terms of this area, we also want to collaborate with our partners and vendors. We want to collaborate with the vendors so they can make or create energy efficient equipment or AI native equipment. And also in terms of next generation communication, we hope on the management and control platform, we want to have a high efficient intelligent management and control platform. In terms of the energy efficiency, we want to build a multidimensional analytical framework so as to evaluate the energy supply and evaluation, so as to close the loop of energy management.
So in the new gen communication system, we use the established AI technique to achieve the closed loop management across the whole life cycle, including the assessment of energy consumption and online diagnostics and perception and warning and strategy generation and closed loop dynamic optimization to realize the next gen communication management. On top of that, we can also realize the multi-device universal energy consumption management. Ultimately, we can realize the coordination between energy consumption, management, and development of the techniques. And lastly, I want to end by saying that China Mobile will lead the green transformation of communications industry with the AI and A6G as the engine. And let's look forward towards a faster, greener, and smarter future networks. Thank you. Thank you, Mr. Gao. As the operator, you have elaborated on AI's application in networks and its energy consumption. Now let's walk on. Mr. Jiang Dajie, Ms. or Mr. Zhang Dajie, Associate Professor at Huazhong Vivo Research Communication Institute, the Director of Advanced Research. Good morning, dear fellow colleagues. Just now, Mr. Gao Feng have elaborated on energy consumption of 5G and 6G from an engineering standpoint. Now, let me share with you from the standard standpoint. My title is 6G native energy savings through collaboration between base station and terminals. So my outline is as follows. First, I will start off by highlighting energy and saving challenges for 5G and 6G. And we will have 3 proposals, including 6G base station energy consumption, terminal energy consumption, and base station versus terminal to collaborate. Despite their contradictions of base stations and terminals. So lastly, I will talk about our synergy, the proposal on the synergistic effect of base station and terminals. And so let's first look at the energy saving challenges for 5G and 6G. So in the testing, we have done some data. We can see 4G and 5G base stations in their different loading. The energy consumption, we can see 5G energy consumption is roughly 3 times that of 4G. That's why Mr. Gao says that the energy consumption cost accounts for 1/3 of the profit, and the main reason is the 5 times increased bandwidth and 3 times of energy consumption, and also the speed of 5G bandwidth is much higher than that of 4G. Therefore, 5G has more frequency point and bandwidth and more channels. And secondly, release 15 initially didn't take into account energy consumption of base station and terminals. So it didn't support that coordination. Now, by R16 to R19, we introduced many versions of energy consumption proposals, including UE and computing energy consumption. But operators have initially adopted the first version. And the second reason is that although many versions have been introduced, the proposals are designed to solve one single problem. There are many redundancy issues. And so given these problems, we can say the comparison of the bandwidth and number of channels. 6G from 3.5 is much higher than 5G, and now it is 200 terahertz or even 400 megahertz, and a number of channels 64 to 128 or even 256. So this means that there are greater challenges for 6G. So let's look at how we can adapt to this energy saving requirements. Now, through GPP, we have standardized some energy consumption proposals for 5G base station. Ultimately, it boils down to a number of things, including the all-domain resources allocation and also the single cell GTS, like SSB and paging. We can use for uneven. So this is for like the air domain, and also for the single cell PIP and the dynamic switch. And here we also want to highlight that for 6G, we can have the dual layer network, and you can see that it consists of 2 layers of network. For the first layer, it's wide coverage, and the second layer is high capacity and high speed, so we can better enable CRTP. So for the second layer, the capacity layer, it can adjust to the dynamic, according to the dynamic load. And so we have 2 proposals. The first layer is low frequency network. Second layer is of higher frequency, so that it has higher capacity and less coverage. So when users have low load, we can switch off the second layer, and then we have IPWA networks, power wide area. And many operators are also wishing to support this technology. They are developing this technology. So in the lower level network, we want to support MPWA and EMBD. And the first level is of wider coverage. And also the first layer is down to network, such as satellite, higher coverage. And with the talking about terminal energy saving technology, I highlight 2 keywords. One is to subtraction, and second is to addition. So for the release 16 to R18, R19, every version has standardized multiple features and network energy consumption reduction. We have some RM and enhanced scheduling. And R17 introduced idle PI, idle state PI, paging, etc. And R18 and 19 introduced low power boost, which supports idle time, idle state, and connectivity state. Coverage. So how to make it wider? We use low power with we use the lower frequency point, such as low 800 megahertz low power woods to weaken the main communication module of 6G. And the other point is that measurement of serving cells and neighboring cells through low power modules. And so by 6G, we can consider use low power woods and use UE for more energy consumption saving to support UE and to reduce blind detection. And we're also considering to combine energy consumption, energy saving, perception, and AI, which is interconnected. So we can see that the sensing assisted energy, we have drafted this mapping or environment restructured information. So with this map, we can use retrition or computing to reduce terminal measurement and reports, thereby saving energy. In the intelligent way, we can use the perceived environmental information or channel knowledge map to reduce the terminal measurements. We can also use AI-assisted energy saving. Just many speakers have shared many cases. So we can use AI to predict traffic distribution and then configure time, frequency, space, and power domain resources as needed. And so in the future, perhaps use AI to predict dynamic and also allocation for better energy saving. So base station terminals are contradictory per se. So we are considering the coordinated synergy between base station and terminal station for energy saving. So DRX, DTX, base station, and UE needs to strike a coordination. So for when during dormant or hibernation, base station and UE are both in hibernation mode. And so this is the first case. Second case, the base station sends on demand, like UE sends a wake-up signal to trigger the transmission of SSB, CSI, RS. So this is an on-demand switch. So UE, through some special schemes like uplink switch signal to indicate base station to switch and wake. So through the schematic design, the base station can have a better hibernation. And the third use case is the low power woods. Now, right now, the 5G supports no model on top of UE. For the 6G, we can consider using this module with main communication module on the base station, so that on the base station there is a main communication module and low power module and main module. Therefore, in the BS and UE, they can trigger each other the main module. And among the device, UE, there can also be coordination between two UEs. For instance, the main module to send the signals. For base station, only low power radio is active, like to receive the signal from UE.
Apart from the three cases I gave you, if we want to overcome the contradictions between the network energy saving and terminal energy saving, or base station energy saving, we need to consider we can actually come up with a new network service to achieve that goal. For example, we can serve the UE when there is no power, and then we can request the network to provide some energy saving services. And also, in the other end, then if the base station want to be energy saving, then probably the base the network can be optimized to adjust the energy saving resources. So also, if we want to achieve that, we need to have good measurement. Energy saving as a service can be provided to users. So we need to validate whether we have energy saving or not. So we need to have a measurement system. So at least it will be able to tell its energy saving to a certain degree. So that's all from my side. I'd just like to give you my summary. So we want to introduce the UE and the network energy saving at the very beginning. And also we need to focus on the necessary attributes and then come up with the design accordingly. And also to solve the conflicts between network saving and the terminal saving, we need to consider the energy saving design at the terminal and also the base station. And also energy saving as a service is something we propose. Thank you very much. Thank you, Mr. Jiang, for giving us the energy saving thoughts on the mobile end. Now, I'd like to invite the last speaker of today in the morning. He's also a young scientist of the city for this forum. So I'd like to invite Zhong Yi, the Associate Professor at the Huazhong University of Science and Technology, to give you the presentation. Dear experts, dear peers, my name is Zhong Yi. I'd like to give you some more information about our carbon efficiency modeling and optimization of solar power and cellular networks. So this is the main content. Now, I'd like to give you the background of our research. Starting from 2015, 178 parties signed the Paris Agreement to limit the global warming to 1.5 Celsius degrees, according to ITU's latest requirement or standards. The ICT emissions trajectories deviate from this target. So in 2020, ITU came up with a long-term goal aiming to reduce the carbon emissions by 45% by 2030. As you can see in this slide, these two graphs talks about the number of 5G base station increase. You can see there are 2.25 million 5G basic stations in China by the end of 2024. Compared with the traditional 4G base station, the 5G base station consumes 3 to 4 times more power. So you can see the total energy consumption in each base station has significantly increased, that leading to a very higher power consumption of the 5G network. Then in 6G is the same thing. So that's something, energy consumption or energy saving is something we must consider for the 6G development. In order to solve the problem, to reduce the carbon emission to reduce the power consumption is not very likely. So we've been thinking, how can we introduce renewable energy in the cells so we can replace the use of the fossil fuel energy? You can see on the slide, those are some the comparison of the life cycle GHG emissions for fossil fuel and also new renewable energies. You can see the renewable energy emission is much lower compared with the traditional energy. So it can even reach the zero emission. So the high power consumption doesn't always mean it will generate high carbon emissions. So a solution is we can use the renewable energy to replace fossil fuel as a way to reduce the network emissions. Introducing renewable energy into the new network face two challenges. First, by using the solar power, it's intermittent within 24 hours of the day, and also it's affected by the weather, by the climate. So there is an intermittent nature in the renewable energy. And also, in terms of the network services, the wireless services or businesses are affected or varies along with the changes of the user activities and also affected by the time and space. So the question is about, or the challenge is about, how can we model the solar power consumption intermittent nature? So you can see here, by providing new energy, renewable energy to the system, we need to have a sustainable power supply, right? And also, there is a fluctuations of the business because of the intermittent nature of the renewable energy, and there is a coupling factor here, and this is something we can optimize and also try to eliminate unmatchedness. And second challenge is the demand and the supply between the multi networks and the new energy network. So you can see these two parts actually are very much isolated. So currently the research on the cellular network is related to the power distribution and also resources management and also sleep mode, things like that in the base station. And in terms of the new renewable energy power supply, with the current research focus is the distribution of the power, planning of the power, or the distribution of the network. So rare work has been done in terms of integrating those two factors and come up with optimization. So that is the area of our work. So what we have done, our team has made evaluation of the carbon emissions in the base station. For example, the equipment, production, the transmission, transportation, operation and maintenance, and also the disposal with recycling of the equipment in the base station. And also the operational and maintenance is also one of the stage or one part of the life cycle of the equipment, and it also involves the carbon emission. So we compare the different stage of the carbon emissions of the equipment in the base stage, and the operation and maintenance is the biggest contributor to the carbon emission for those equipments in the base station. So we try to optimize that carbon emissions in that stage, right? So the traditional method is to use the carbon emission factor method. So you use a certain amount of energy, for example, and then you turn that into the carbon emission factors, and then you can calculate the carbon emission. But actually, the carbon emission factor is very different from different type of energy. And also, we study the carbon emission efficiency. So how much benefits we can collect during. So we study the energy efficiency and also carbon emission efficiency. So it's BPS per kilo. That's the unit we use to describe carbon emission efficiency. And we come with several key indicators and its relation with each other. So you can see the relation on the right side, and you see the trade-off between the carbon emission efficiency and the energy efficiency. It's not simply a linear relation. So after you introduce the carbon emission factor, the correlation is not in a singular relation. So we need to model the relation, a very complex relation, and then to optimize the carbon emission efficiency. And we come up with this concept of carbon neutral cellular network. There are 4 layers. So for example, some solar power or wind power, and also the battery is being used like energy storage, and in the third layer is communication network. So the first layer is energy generation, the second layer is the energy storage, the third layer is communication network, and the fourth layer is application. So we need to have a module to optimize different functions in the 4 layers. So you can see on the right side there's a diagram, a module for carbon. So that's what we said, carbon neutral network management. And within this network, each base station is equipped with solar generation and energy storage systems. And the energy storage battery, it provides backup power, and it can will also provide the power backup, so it can be connected to the traditional grid if there is no sufficient power from the renewable energy, and so it can stabilize the power supply. So when the renewable energy is not sufficient, then we can use the municipal grid power. Also, after introducing renewable energy, each module we have an evaluation of the full life cycle assessment of the carbon emission volume, and then you can see this is the table of that evaluation results, and it involves the analysis of the carbon emission in the cells, in the base station, in the terminal, on a mobile phone, things like that. And then we have some optimization work. We established a solar energy generation model. You can see the solar power is quite intermittent during 24 hours of the day, and during the noontime, it peaks, right? So we come up with this formula or this model so that's the 24-hour variance of the solar energy. And also we studied the spatial variation, temporal variation, and also in terms of the energy storage system model. This is the model, and we come up with this model, and we also introduce some constraints or restraints during the charging and decharging of the battery. For example, there is a threshold you cannot surpass in terms of the storage volume. And in terms of the cellular network energy consumption in the base station, so the base station consists of multiple transceivers, and also we analyze the power consumption of those things, and we also come up with the model. And when we have a microgrid, in terms of the energy sharing, we also come up with a model. As you can see here, there are some mathematical models about the energy shaping. Also, there are the constraints or restraints about the energy shaping model. In the model, in terms of the energy efficiency, carbon emission efficiency, we use the carbon emission factor method. Then we come up with this carbon emission model, and then we'll calculate the benefits we collect in the system. So we calculate the throughput model, as you can see the formula here. Then finally we can calculate the carbon emission efficiencies, and then we can optimize that efficiency. As you can see, the optimization comes in 2 parts. First part is optimization in the renewable energy network supply. So we optimize the energy distribution, allocation, what's the best allocation method. In terms of the optimization in cellular network, we study the optimal power allocation method, and that is the strategy of scheduling and also allocation of the power. So that's how we optimize the carbon emission efficiency in the network. Also come up with some key KPIs or indicators. And you can see there are some constraints for the optimization. And as you can see here are some computation processes, but I will not dwell on that. And also here, through optimization, we have got some preliminary numerical results, as you can see on the chart.
On this graph, you can see the traditional power consumption as the y-axis, and the x-axis is 24 hours along the day for the x-axis, and it's very hard to combine. So as we directly combine the new energy capability with the networks, and this is the changing curve. And after optimization, we can see that for the power consumption is indicated in red of the grid, and the power consumption of the grid is reduced up to 38%. And during the noon, there is the highest amount of solar power, and so the power consumption is reduced by 38%. And so we can see the maximum improvement in carbon emission efficiency is up by 64% after optimization. So the blue indicates before optimization, and the red indicates after. During the noon, the peak improvement is up by more than 60%. And so we can see that the carbon emission curve is not linear. At the noon, the carbon emission is the most even one, and due to the introduction of the new energy. The last graph I want to share is the platform, solar-powered cellular network hardware platform we built in our lab, including software and hardware. For the hardware, we can see the inverter, the DC inverter, and we can see also some frequency units. And we have also designed the workstation for control to collect the information data of the operation to control the system. And so this laptop is being used as the workstation to control the software and monitor the operation of the system. So that concludes my presentation. Thank you so much for your time.
All the keynote speakers, and they are excellent presentation. And currently, we are coming to the last section. It's panel discussion. And in this panel discussion, we included some of the famous professor from the Li Yucai, the head of the Shanghai Nokia Bell Company, the Professor Yang, Associate Vice President from the HKUST, Professor Tomoaki Osuki from the Keio University, Japan, and Professor Xu Chen, the Director of Institute of Advanced Networking and Computing System from the Sun Yat-sen University, and the Professor Jianhua Tang from the South China University of Technology, and Professor Lin Tian from the Institute of Computing Technology, Chinese Academy of Sciences, the Hong Kai-xiong, distinguished professor of Shanghai Jiaotong University. Let's welcome all the professors coming to our panel. Please. Okay, thanks all the professor and the experts. They are also come from the university and also from the industries. I prepared 7 questions and are already listed in the screen. So according to these questions, I start my question. I hope to get some response from these excellent experts. First question is how to overcome the challenges to communication service brought about by instability of green energy. If possible, Professor Yang, could you answer this question?
Okay, thank you very much. I learned a lot from this morning's talks. I think Mr. Gao Feng mentioned in his presentation that green energy has this kind of unstable problem, and we always see the dynamics of green energy. So he mentioned that we should concentrate on the distribution and also transmission of this sustainable green energy. And I firmly believe that we should make use of these dynamics to benefit the communication network. Also, inspiring me this morning is Professor Xiaoyong's talk, and also he mentioned that carbon emission is not directly associated with the amount of green energy. Sometimes you need to pay attention to the amount of carbon emitted to the environment. So we can also make use of this different type of energy to minimize the carbon emission for future 6G services. So my answer to this question is that we should do this step by step. We should not replace the current energy structure totally by using green sustainable energy, but we need to consider the availability of green energy, like in Professor Xiaoyong's talk, he mentioned that in the US, in different season, different region, you have this large scale and a small scale dynamics of green energy. So we can use these statistics to optimize our energy efficiency in the network. But we should not use 100% of the energy totally supported by the sustainable energy. We should, for example, 10%, starting from 10%, 20%, we need to see how sensitive that your network and the service is affected by these dynamics of green energy. So this is a new research topic that we should make use of the existing data in energy supply, and also in this green energy study to better serve our purpose in the 6G networks. Thank you.
Okay, thank you. Thank you, excellent response from Professor Yang. And the second question is, how will green communication be implemented in the 6G space communication system? Professor Osuke, if possible, could you answer this question?
Okay, thank you. So I'm very happy to be here. So some already important issues already addressed in the previous talks. Although I cannot understand Chinese, but I guess, yeah, probably I could recognize. Anyway, so first I want to say the space communication, so very big advantage. For example, the global coverage and also the disaster resilience, or I can say resilience. But of course, you can see the many challenges there are, such as, of course, related to this one, green, right? So then, yeah, of course, like energy efficiency or solar power, I mean, satellite is important. But we need to consider, depending on the altitude, so then life cycle of the satellite different. And also the link budget is different. Then we usually say space communication. Yeah, of course, LEO Starlink is important, but not only. Yeah, of course, many years GEO already used, and also the MEO sometimes. But also particularly in Japan, we are now discussing and preparing to start the HAPS service, high altitude platform system. And also China very good at also the UAVs, right? So then each different attitude, different coverage, and also the different life cycle of the each plane. And also the most important one is different, life cycle also the link budget. Then, so the already many, professors, also the people from industry presented scheduling, also the joint optimization, very important. For example, the Leo is okay in some application in 5G or even a 6G, but we have to consider the latency in some applications. Hubs can provide, of course, the coverage becomes smaller, but still much larger compared with the terrestrial system, and also the much lower latency than LEO. Those kind of things we need to consider, and in order to, allocate and reduce the energy consumption. Of course, AI also plays a big role in 6G space communication. So also each country has very, good at a different field. For example, China, good at many satellite systems. We are also good at small satellite design or chips. So in such a sense, so 6G space communication important, and international collaboration is also very important. That's my point. Yeah, thank you.
Thank you. And then the third question is, in the era of AI, the core carrier of applications and the service of 6G will no longer be apps and wafer sites, but AI agents. In the near future, larger models will even replace architecture design and chip design, and communication is inevitable to integrate with AI like DeepSeek. And this feature trend will overlap with the deployment time windows of 6G. How to design 6G to support future massive AI service and applications? Professor Xiong, could you help to answer this question?
Thank you. I noticed some reports to mention how to use artificial intelligence to enhance the communication technologies. But from the AI's perspective, how to make concrete communications with the information. From artificial intelligence, the information may be generated by approximation distribution, not rather than the fidelity communication. That means that the information only generated by, we approximate by the distribution. That means that we can using diffusion generation or use a prior diffusion, means that. So the communication may be have a revolution in the future. Means that everybody have a large model, transformer, something like this. And we can, in the latent space, we can exchange the token in respectively large model, the transformer means that. Then we can approximate the alignment, the tokens in every person's the models, the transformer models, then we can generate in different user equipment side. So that means that, so maybe in the future, every person have a own transformer model. Means that then we can we can exchange the tokens alignments in the latent space. So in the future, it means that this is a very, very interesting perspective. So we can design a communication system. So for the devices production or the our users, our customers, maybe contract with own transformer models, large language models, yes. And we can train every day. We train our own models, and we can alignment different models. That means that's communication in the future. Thank you very much.
Thank you, Professor Xiong's response. And the fourth question is, AI is a key enabling technology for future 6G system. However, AI is computing intensive and demands significant energy consumption. How to improve the energy efficiency of AI in order to achieve the green AI? The Professor Chen, could you help us to respond to this question?
Okay, thanks for the invitation. It's my honor to join this forum. As for this question, actually, yeah, indeed, Edge AI will become more and more important in the future city system. As just mentioned by Professor Xiong, in the future, maybe every user has his own LLM models. So in this case, we need the Edge AI technology to well support such application or scenario. But indeed, the energy efficiency of Edge AI will be a key issue, as the computing of AI model and service will demand a lot of energy consumptions. In my opinion, there are multiple perspectives we can consider to improve the energy efficiency. First is the algorithm or the model perspective. For example, maybe in the future, we need to develop more efficient model lightweight technology, such as the LLM compressing technology or other kind of technology in order to make the model more efficient at the edge environment, but with a smaller model size or much less computing resource demanding to support such applications. Second, we can also explore a new line of design, a new line of model architecture, such as member architecture or say the neural-inspired computing architecture, such as the spiking neural network or hyperdimensional computing model. This kind of a new brain-inspired or neural-inspired computing models, maybe, which can be much more energy efficient and can also be very useful in many Edge AI applications. Third, maybe we can consider to explore the hardware perspective. For example, we need to consider to design domain-specific hardware, such as new TPU or LPU language processor model in order to support this LLM application at the edge, in order to boost the energy efficiency rather directly using the GPU, this kind of very energy efficient and very energy consuming hardware. Last but not least, I think it's also important to explore the edge and cloud collaboration, this kind of approach with the integration of the green energy. In this case, we can develop a pervasive and green computing power network system. Then we can decompose compress AI tasks into, say, multiple sub-AI tasks, and then we can schedule this kind of tasks, say, according to the carbon emission intensity across different area, different location, in order to achieve energy efficient scheduling in the whole system perspective. So that's my answer. Thanks.
Thanks, Professor Chen's response. And the fourth question is, what are the challenges faced by the radio access networks in 6G from the perspective of green and sustainable development? And what are the possible ways to solve it? Professor Tang, could you help me to answer this question?
Okay. Yeah, thank you, Professor Ge, for your invitation. Okay, before I answer my question, I think I'd like to share a very interesting story or a very interesting report I just read several months ago. The report said that there's a very famous soccer player, Cristiano Ronaldo. He has more than 200 million fans in the social network, and there's someone do a very interesting calculation. Say, if Cristiano Ronaldo wants to upload a picture in the social network, and for the fans, if all the fans wants to receive the picture, wants to just download or just want to watch the picture, to see the picture, the power consumption is about 24,000 kilowatts hour. This is a very huge number, 24,000 kilowatts hour for just one picture for these famous guys. How huge is this number? Let me just do an equation. Say, this number, 24 kilowatts hour, equals to a person, a normal guy, can live for about 24 years. Okay, that means for just one single picture, for this famous guy, just upload one single picture, the power consumption, the energy consumption equals for the normal people to live for 24 years. So this is a very huge number. And that means the power consumption or the energy consumption is not only related to the operators, but also for normal people, for everyone. It's a very key issue in the society or in the next generation communication. So from the radio access network aspect, as we know that in the network, the bottleneck part always happen. The bottleneck part always happens at the radio access network, and from 1G, 2G, 3G, 4G, 5G. So for every generation, I think we always do the main modification at the radio access network or the RAN side. So there are many challenges in the next generation technology. I think the main challenge is that we have to see the trade-off between the performance and the energy consumption. This is the main issue, as just introduced by the expert from Vivo. Say from 4G to 5G, we have about 5 times bandwidth increasing, but we only have 3 times power consumption increasing. So this is kind of development, but still cannot reach the goal. So in next generation, in 6G, we still have to face the problem that we need to do the trade-off between the energy consumption and the performance. For example, for next year, we need the higher spectrum, and we need much more dense base stations. So all of these aspects will introduce much more energy consumption. How to solve this challenge? I think we can also try many different ways. For example, we may try to develop some advanced algorithms. We may try to develop the renewable energy powered hardware, as just introduced by Professor Zhong. Say it's possible to deploy the solar powered base station in the next G. And also AI is quite important. There's a very interesting concept, the AI RAN, the AI radio access network, and I think there's a demo, very interesting demo in the first floor, developed by Sun Yat-sen University and Singapore University of Technology and Design. Yeah, if you are interested, you can just go to the first floor to see the demo, the AI RAN. It tries to do the full integration between AI and the RAN. Say from some aspects, AI for run, AI on run, AI with run is very interesting. So, the main difference between AI run and the previous run is that we want to use GPU to finish some of the function for the run. This is a very interesting concept because for previously run, we always use some specified circuit, specified chips, and maybe we also try to use some general purpose processor. We use GPU to replace some specific chips, but for AI run, it says we can use GPU to finish most of the run service, the run functions. It is very interesting, and also it's very challenging to achieve this goal. And if we have AI run, we can save the energy for next trip. We can use AI to predict the traffic, to turn on or turn off the base station based on the traffic. And we can also integrate more advanced AI algorithm, AI method to reduce the power consumption, to reduce the transmit power, to reduce the delay. So there are many aspects we can try. And yeah, that's my answer.
Thanks, Professor Tang's response. And the sixth question is, how about AI for green communication? And what can a company do for this application? So this question I left for the Dr. Tsai from the industry company.
Okay, thank you, Professor Ge. So I think we can give some perspective from our company, from a system vendor company's point of view. So the AI, so I think that the role of the AI for the 6G, I think can be twofold. So first, I will share the view on the role in the for the network operation perspective. So I think so for to enable the autonomous network operation and to reduce the energy consumption for the network, so the AI can play a very significant role. So based on the artificial intelligence algorithms and empowered with the AI agent, so we can leverage the AI agent to better predict the traffic pattern, to analyze the network condition, and to predict the power supply condition, so to make a better decision on how to optimize the network operation. So according to our current exercise, so as Professor Gong indicated in his talk, so we have successfully verified the AI-aided scheduler to optimize the operation of the small cell, so which have already achieved the 30% energy efficiency. And in addition, in our recent practice inside the Shanghai international circuit, so the Formula One races, so we have worked together with operator to use the AI agent-based approach, so to better understand the service requirement to make the a very short-term prediction of the traffic load of the network, so that we can smartly adjust the power to, for example, antenna the tilt angle, and to optimize the threshold for some traffic control, so we can achieve the, that's the case for the macro cell. So for the macro cell, so we have achieved in the recent practices, we have achieved about 10% energy efficiency increase. So in addition, so the time for the time saving is increased by 2 times based on our some recent progress. So that's some very powerful application to aid the network operation. And on the other side, so another important role is for the AI to improve the AI interface in the run side. So, for example, so we know that so the alpha side actually is the most power hungry part inside the network, especially in the if we will apply the mass MIMO, for example. So, but if we have to have a higher power efficiency, so on the other hand, we would like to make the power amplifier to work in the high power region. So, but in that case, so that it will lead to very significant nonlinear effect. So the high distortion. So to solve this problem, so we in the AI interface side, so we have already tried to use the AI-based algorithms, signal detection, deep TX, deep RX algorithms to do smart signal digital pre-distortion and the smart receiver, so that we can have better make the algorithm to the AI interface to better mitigate the nonlinear effect to improve the sensitivity of the signal. And another one I think is to make the AI to serve for the MIMO operation. So, for example, to better improve the beam scanning efficiencies. So we have successfully utilized and improved algorithms for the hybrid MIMO, hybrid beamforming-based MIMO system. So have already achieved the at least 3 times energy efficiency compared to the current state of the digital based beamforming algorithm. So that's some of our recent practices. So we believe that so the AI should play a very significant role in the future 6G. Yeah.
Oh, thanks, response, Dr. Tsai. And the last question is, what are the opportunities and the challenges of computing and communication integrating in green communication? And this last question is last for the only madam in our experts, Professor Tian. Could you help us to respond to this question?
Okay, thanks, Professor Ge. I think the integration of computing and communication is a technological trend in 6G, and it can provide the effective way to our green communication. For example, seeking the computing resources in our wireless access networks, the data processing can be closer to our mobile terminals compared with it is processed in cloud, so it can reduce the energy consumption and transmission bandwidth. And many experts mentioned the AI combined with 6G in the future. I think it is a kind of the integration of computing and communication. It can reduce the energy consumption and improve our performance of systems. And I think especially in the resource constraint scenarios, such as connected vehicles and drones, it is especially useful in these scenarios. And there are many challenges in the research of the integration of computing and communication. I think one is security, because many data is distributed in the wireless network or many mobile terminals. This is a challenge to the data privacy and the when we use a model training in this research. And another challenge, I think, the macro optimization with energy and some speakers mentioned the carbon carbon emission and our communication. For example, the AI algorithm can improve our communication systems some performance. However, the energy consumption of this algorithm may be higher than our traditional algorithm. So I think this can we should research this how to balance the energy and the performance of the different algorithms. That's my idea. Thank you.
Thanks, Professor Tian's candid response. And all of my questions have been responded. So, is there any other questions from our the visitors and attenders to ask our experts, panelists? Okay. Thank you, everyone. And our forum is closed. Thank you, everyone.